Hello, I'm Andrew Drinkwater. I'm from Plaid Analytics, and I'm here to talk today about how Tableau relationships and level of detail expressions can help us understand different patterns of behavior. Generally speaking, we'd be looking at things like which particular actions led to a general change. In the specific video today, we're going to focus on a higher education use case around which courses did a student take before changing their major. So oftentimes, we assume that a student goes to a university and they complete a degree in 4 years, and that's fairly straightforward. We assume they take 5 courses per term in the fall and the winter, and they repeat this pattern for 4 years. However, the reality is often more nuanced. At most higher education institutions that offer degrees in North America, it takes 4 to 6 years to complete a credential. And the pathway is seldom perfectly linear. They might change to a new program, as we see here in orange, or they might exit from the institution entirely. Now, this may not be a bad outcome for the student. They might well change from a university to a polytechnic. Let's say they discovered that they actually wanted to be an electrician instead of an engineer. This is a good outcome for the student, though it can present some challenges for the institution that would be losing a student who may need to find new students to fill that seat. And their course taking patterns are also more nuanced. We can see here with the orange blocks that not every student takes 5 courses per term. In my own case, I took 6 courses per term in my first year and discovered that was too many. And I gradually wound down until I was taking 3 courses per term, similar to what you see at the bottom here. But at the end of the day, the student still needs to take an average of about 40 courses or 120 credit hours, 3 credits per course in many cases. So they still have to complete those, just the patterns get moved. Maybe they take courses in the summer. Maybe they take a term off to go on international experience, such as exchange, or maybe they participate in cooperative education or another form of practicum or internship. And so then in order to get their total number of courses up to that 40 that's required, they need to take some additional courses. And in this case, we're showing an example where a student takes their 5th year relatively full-time and their 6th year just 2 courses. Now, this might not be entirely because of student choice as well. It may be possible that the courses that they needed were not offered in a particular term, or they were full. So they may also have discovered that some of the courses, quote unquote, did not count for their purposes. And they had to add those in at the end as well. So back to our example. Where this came from was a client that I worked with who was wondering about changing a program from entry at the 3rd year to entry at the 1st year. So rather than being a 2-year senior level program in Bachelor of Education, it would be a 4-year program spanning the entire 4 years that a student studies at the institution. The students could take anything they wanted in the first 2 years, generally speaking, up until now. But since the program's developing a curriculum for those first 2 years, they wanted to know what students who have moved into education already were actually taking in their first few years. Maybe there's information from those students that could be helpful for planning a curriculum. And then oftentimes we hear, oh, we actually don't know which courses students took before they moved into our program, because the data can be hard to surface sometimes. Well, as I'm sure you've guessed by now, Tableau could probably help with this problem. So what we're going to try and answer today is what are the top 10 or 15 or 20 courses that students transferring into the Bachelor of Education program completed. And just by way of example, here's where we're headed. We want to create some visualizations that help us understand which courses they took. And for the Bachelor of Education, we're looking here in the middle. For perhaps some more interesting patterns, we can look at Bachelor of Commerce as well on the left. So let's break down this problem into some key questions. The first one is, in order to figure out all of our following questions, when were they first admitted to our university? In this case, we're going to use an example database that resembles PeopleSoft. So we can see here in our answer section that we have a table called PS Student Career Train. And this table helps us understand what primary program a student was enrolled in a particular term and number of credits they completed, grade point average, other important metrics like that. This example is simplified a little bit. We only have students in a single program at a time. Many institutions, this is not the case. We've also glossed over effective dating and simplified those for the purpose of demonstration. If you work with a PeopleSoft school, you'll want to work on the nuance of this. Next, we want to know what program they were admitted to when they first enrolled at the university. We then want to know, are there any students who've changed majors? As in, they have the presence of more than one major on their academic record. Next, we want to figure out what term did they begin studying in that new program or major. The first four examples here are all answered effectively by level of detail expressions in Tableau. The fifth question focuses on Tableau's relationships. The last question, and really the key for our example, is what courses were they enrolled in before that transfer term? We use a Tableau relationship to answer that, in part because the courses they were enrolled in are more granular than which programs were they in a particular term, which is what we find from the student career term table. Good afternoon, my name is Andrew Drinkwater. I am the president and co-founder at Plaid Analytics. We're a Tableau partner, and I am an expatriate enrollment forecaster from one of the world's top research universities. I hold an MBA and a graduate certificate in visual analytics, and I've been using Tableau for a very long time, since version 3.0, before Maps came out. Plaid Analytics enables enrollment leaders to actively plan for the future with a strategic enrollment management data and analytics platform, which includes enrollment tuition forecasting, data governance tools, data warehouses and pipelines, and of course the visualizations necessary for your decision makers to use them. So to start with, most calculations in Tableau allow you to compute values at the data source level or the visualization level. So data source level includes things like row level calculations. Visualization includes table calculations as a generalization. Level of detail expressions allow you to compute values at multiple different levels. You can be more granular than the visualization level, which is typically an include expression, or you can be less granular / more aggregate. And that's typically an exclude expression. A fixed expression allows you to be kind of anywhere on this spectrum that you choose to be. You define the granularity. We've got some additional presentations on Tableau relationships. You can find them here. In Tableau, there's a number of different ways to combine data. We'll start with joins. These have been in Tableau since the earliest days. Joins allow you to combine two tables and output a third table, and you can stack many joins together. So you can have multiple inputs and a single output. There's two different kinds of joins. So if we think of row level joins, we can have two tables. On the left, we see institutions in Alberta, Canada, and Quebec, Canada, and Ontario, Canada, with the number of students that are enrolled in them. And on the right, we see population of those provinces as of a census in 2016. This is a little outdated now. From this information, we could create a table that would allow us to answer questions around provincial participation. With a row level join, it would look something like this. You may have noticed that our column on the right for population has doubled in the cases where we have more than one institution in a particular province, such as with Alberta and Ontario. To get around this, when we go and aggregate our data, we can see that this doubling effect has actually come into play for our sums. And so the population of Alberta and Ontario here is showing us higher than it otherwise should be. We can get around this to a certain extent by using aggregate joins. So if we aggregate our table on the left so that it's at the same level of aggregation as our table on the right, then when we go and do our join, all our numbers are correct, but we've lost the nuance of these individual institutions on the left. The advantage of aggregate joins is there's many different ways that we can put them together depending on the contract that we suggest to the table in terms of how those are related. And this forms what I believe to be some of the background of where Tableau relationships come into play. Relationships themselves are a dynamic, flexible way to combine data from multiple tables. They describe how the tables are related, but they don't merge the tables together until you need them. You can think of a relationship as a contract between your two tables. So how they're related, what fields they're related based upon, and Tableau will use that contract in order to build the right query for the view that you're looking at in real time. You might want to consider relationships because there's less data preparation and you can use them to answer more questions per data source. You can also combine different levels of granularity, which is what we're looking at today. And this can help promote greater trust in your data because there's different ways to put it together and you're less likely to run into challenges around aggregation or loss of data. So relationships allow you to bring together multiple tables at multiple levels of detail. They're highly flexible, and the joins themselves, which get done after the relationship part, are created on the fly based on what you're using in your visualization. At a really high level, some of the differences are that joins are done at the physical level, as in they exist in your database, but the output is a logical table. So we combine two tables A and B, and we output table C. We fix the join type when we create the data source in Tableau. The queries are executed when you create the data source for a join, or as part of a live connection when you make a change. Extracts can be pre-computed as well. In relationships, the level of detail of them is aggregated as you go. The input to them is logical tables, which we'll talk about in a bit. The output is a definition for how to use those tables, but the joins are actually created based on what's on the visualization and implemented on the fly. In terms of the queries themselves, with a live connection at any rate, only the tables that are used in the visualization are included in the query. If it's an extract, the same principle applies, but you're querying your extracted tables instead of your live tables. Extracts themselves aren't pre-computed and are joined at runtime, but the data itself is pulled into an extract. We won't talk much about blends today, but this is an alternate method. Blends are applied at an individual worksheet level. They cannot be published as blends themselves. You have to blend them on the Tableau server, as an example. And there is a very strong notion of a primary and a secondary data source with blends, unlike with relationships. Blends are essentially an aggregated left join that's used, and they're computed locally. So let's get into an example. Let's imagine you work in strategic enrollment management in a university or college, and we're trying to figure out something like, are we going to meet our admission targets? Anything versus targets is almost always a good example for relationships. So here's the general model. We have two logical tables that we've defined, A and X. And contained within those are the physical layer. They may have one, as we see on the right, or many tables that create our logical table. So let's take that to our example of applicants versus targets. So we've put targets on the right, applicants on the left. Targets are made of a single sheet. In fact, it's an Excel sheet called intake targets. So that's our logical table, targets, and our physical table is the same. However, for applicants, it's a little more nuanced. We have an applications table that's joined to a program table to help us understand what, say, BCSHS is, a term table to help us decode cryptic term codes, and national status to help us understand domestic versus international students better. We have a contract that relates these two things. As an example, it might be admission year and basis of admission, or admission year and admit year level would relate our applicants, which are super detailed, to our targets, which are really high level. Similarly, if we look at students and programs and terms on the left, which is not very detailed, and students and courses on the right, which is very detailed, we can use a relationship to bring them together. So students in programs and term is one row per student per term per program that they're enrolled in. And there's 4 tables that make up that information. The students in courses, however, is one row per student per term per course that they're enrolled in, and 2 tables make up that information. So by way of comparison, let's simplify and say all of our students are only in one program at a time. So on the table on the left, we have 1 row per student in a term, and the table on the right, we might have up to 5 rows per student if they're taking 5 courses. If we were to join these in the conventional fashion, we might well end up with 5 rows per student, messing up our head counts. However, with Tableau relationships, we can actually bring these things together properly and maintain that information around aggregations at a proper level. So we're not going to overcount our students, for example, and in turn, we're going to be able to identify when they change programs. But we're also going to be able to identify which courses they enrolled in every term, including those that happen before they change programs. Outside of the higher education context, maybe things like what factors led to an employee changing jobs, or what behaviors, such as credit card spend and flights, led to an increase in status with an airline. More generally, what micro behaviors led to a more macro change. Some rules of thumb to keep in mind. It's good to use joins if the secondary table is less than or the same granularity as the primary table. It's also good to use joins when you have no duplication or loss of data if you use an inner join. If you do have duplication or loss of data, you might want to consider a relationship. Consider a relationship when the secondary table is a greater than or different granularity from the primary table. An exception to this is that lookup tables can almost always be joins. So if we have a program lookup table, that can be a join because there should only be one program description for one program code that lives on our primary table.